I think that's the right one. Yeah, that's the right one, isn't it? Okay, well, welcome back. I think we lost about 4 people during the break, which is very impressive. And I'm very pleased that you've all stayed with us so far. I hope that will continue for the next 30 minutes at least. This session is a little bit different from the first session, in that we're talking about, well, certainly in the first 2 talks, we're talking about sort of real engineering problems. So I'm going to talk about electric planes, and the second talk by Jamie Gowith is about fusion. Now, both of these have very, very big barriers to overcome, extremely big barriers to overcome. But we'll give you a flavor of what's possible. We'll give you a flavor of what's been done and what we might do going forward. So electric planes have been around quite a while now. Not as long as electric cars, believe it or not. First cars were actually electric. They predated petrol cars. And there was one of the main milestones was to build one that went any distance at all. So this is a picture of EFAN, and in 2015 it successfully crossed the channel, which Louis Blériot had managed about 106 years before. So you can see how far behind electric planes are, and maybe how far we've got to go. Hopefully not another 106 years. So EFAN then became EFAN X. And I'm going to show you a little video of EFAN X. Airbus and Rolls-Royce like doing promotional videos. I don't know whether the sound's going to play on this. Nadia, is the sound going to play on this or not? Well, let's try and see what happens.
Tim, if you just pause it there and press share screen.
Yeah.
Little arrow. Yeah. So if you go to the share screen and there's a little arrow.
Downward arrow.
Yeah, and then click advanced sharing options. There should be an option to share the sound.
Advanced sharing options. Oh, there you go. Sorry. Yes, do apologise. I've missed that before. Thank you. Sorry about that. Okay, I'll start again. Can you hear it now?
Yeah, we can hear that.
Okay.
In 2014, we saw the revolution in electric propulsion in other industries, in particular automotive, and we were convinced that the electrical revolution would happen in aerospace as well. So we launched a fully electric-powered aircraft, which we called the EFAN-1.
The original EFAN project really deserves a lot of the credit for convincing the aerospace sector as a whole that electric and hybrid electric flight are a viable and an inevitable future for our industry. Nobody believed in it 5 years ago.
In early 2017, the technology was moving much more quickly than we expected. So we took the decision to start a much more ambitious program called the EFAN-X.
We are pushing current technologies very much to the limit.
The first challenge to be addressed with the EFAN-X program is to bring those components to aviation safety standards.
Ultimately, for me, the success of the EFAN-X would be to be the first to fly a 2-megawatt electric propulsion system on an aircraft in the early 2020s.
Okay, so the eagle-eyed amongst you will have noted that the first flight of the EFAN-X was scheduled for 2021. unfortunately, they cancelled the program. So it isn't going to be there. It was cancelled last year. So that program itself has been cancelled. It doesn't mean that Rolls-Royce and Airbus are no longer interested. They are interested. But his hope of demonstrating a 2 megawatt motor on an aircraft by 2021 is not actually going to happen. They are carrying on. They have this program, the Echo Pulse, and that completed wind tunnel testing relatively recently. So it's sort of in abeyance. So where does the picture move to from there? Well, Grant Shapps told us last week. Grant Shapps, I don't know whether he reads his own press releases, but I'll take the privilege to do it. He says, aviation has a vital role to play in tackling climate change, which is why the government is today also launching the Jet Zero consultation, which commits the sector to a net zero emissions target by 2050. So far, so good. That's not a problem. That's not a problem at all. Trouble is, if you actually click on that link to Jet Zero and you look at the kind of people they're talking to, it's probably unlikely that UK domestic aviation will reach net zero by 2040. And I'll show you why in a later slide. There's the consultation. That's what they want to do. That's on the left, you've got the megatons of carbon dioxide. And what will happen if we do nothing? Well, they haven't updated this for COVID much, I don't think. But basically, it will just roughly get on for double by 2050. If they have high ambition, if they have substitute aviation fuels. I mean, high ambition with the breakthrough on substitute aviation fuels, I don't think solves the problem. It's the lowest one on their predictions, but all it does is move the problem somewhere else. So, you know, you probably would have to grow your jet fuel or something like that, which would give you other problems. But that's what they're predicting. They, unfortunately, as I say, they depend on some information which I don't think they probably properly peer-reviewed. And I do apologise if anybody here from the Wright Motor Company is actually listening. But buried in the document Grant Shapps referred to is a reference to something called the Wright motor. And according to their vision, they will be able to conduct motor ground tests this year and enter into service by 2030. They're going to lower the weight by 75%. They're going to use up to 6 times existing voltage. Now, if you just work out the problems with actually increasing the voltage by 6 times, when everything has to go through all sorts of tests, etc., 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 it's just not going to happen. So the government thinks that these things exist. It's up to us to educate the government because they don't, I'm afraid. None of that data, I believe, can be backed up or has been backed up. With the proviso that obviously I am not actually on the ground with Wright, so I may be wrong, but I frankly doubt it. So that's their vision. That's what they think will happen. And they are partnering with EasyJet. They think that we will have a 180-seat aircraft in service by 2030. This is a more realistic time plan, but even this is probably optimistic. So you can see that we do have, I mean, you saw with the EFAN, we have small aircraft and of limited range. As batteries improve, you'll be able to increase that range. You can increase the range and increase the range, but then you get a break. There are arrows between the first set of blocks, but not the last set of blocks, because the last set of blocks represents a complete change in technology. The problem is that everybody bandies numbers around for the power density for motors. And they all say, oh, well, it's got to be a 2 megawatt motor and it's got to be 20 kilowatts per kilogram. But Archie Campbell, God rest his soul, would be turning in his grave if he could hear them say it, because physically it's not possible without a complete change in the technology you're using. Just existing magnetic materials and existing conductors can't do it. So if we're going to match that timeline, and I would argue that that should be 30, not 20, then we need superconducting motors. In addition to superconducting motors, we need an awful lot of work. Now, this is a group which I co-founded last year. And we've been looking at all the problems that you need to overcome in order to electrify aircraft. So this was a series of workshops. One of them actually is happening now, literally, as I speak, and I can't attend it. But we identified all the different areas where we need solutions. And we've been discussing, and this is all open access, and we will be publishing all this data. And I invite anybody who's interested to participate in this program, because I think it's rather important to actually consider properly what we need in order to bring out electric aircraft. Notwithstanding superconducting electric aircraft, just electric aircraft full stop. Okay, so sorry, that slide's got a bit wrong, but this is a graph which was produced by a friend of mine, Fred, in Airbus, and he produced it some time ago, and he hates it because he says it's too complicated, because actually it's got multiple axes. So you have cryocooler power density, you have tank gravimetric efficiency here, you have machine power density, and at the bottom, although I can't see it, can I see it? Yeah, you have machine inefficiency. So the two numbers you really want to look at are the machine power density and the machine inefficiency. And the other thing you have to look at is the areas which are green. So the areas are green, when you can get into the green, that means you're good to go. So you can see that's where the 20 kilowatts per kilogram figure comes from, because that's where the green starts appearing. Below that, it's just not going to work. But the real killer is this number. Really, what you're trying to do is you're trying to improve the efficiency to such an extent as has never been done before. And to achieve this kind of number, you need to produce an all superconducting motor. If you haven't got an all superconducting motor, you're down here. In fact, probably down here. So you need all superconducting, but if you've got all superconducting, you've got a problem, because almost all superconducting motors are half superconducting motors. And the reason why they're half superconducting motors is because superconductors have an annoying habit of having high AC losses. So you make them half superconducting motors, so they're operating in synchronous mode, and the rotor just doesn't see a changing field. If we're going to get anywhere near this, we need to make a fully superconducting motor. If we're going to get anywhere near this, we need to make a fully superconducting motor where we've improved the efficiency by probably, or the inefficiency by probably an order of magnitude, or possibly even more. So this is a massive challenge. So I told you that EFAN X had been cancelled or suspended or whatever they want to call it. There is a lot of work that's going on, though. The Americans are moving ahead. They have the so-called RPE, which was announced last year. And there's two elements to this. They have really clever acronyms. Well, they're not that clever because they've really sort of bent over backwards to try and create the acronym. But basically, it's two programs. It's Ascend, which is motors, and it's Reach, which is essentially batteries. Both programs are interesting. If you look at the Ascend program, and if you're interested in looking at the program, you can just shine your smartphone at that grid, and it will take you to the page, or you can click that, write down that link. If you're interested, you can look at the program, and superconductors do, surprise, surprise, feature in the Ascend. So there's the description of the program. I'm not going to read it all out, but basically they're being a little bit more conservative. They're not shooting for the moon just yet because they're going for 12 kilowatts per kilogram. The reason why they're going for 12 kilowatts per kilogram is because they're including some conventional technologies in there. So the conventional technologies would simply be barred if you're going to go for the 20. And again, efficiency at 93%. This is really quite not particularly ambitious targets. And if you believe Fred Berg, they won't get you to a final solution, but it's a start. And they're investing quite a lot of money in doing it, and they have a lot of partners. There are lots of programs in there. There are lots of people who would be familiar to you guys in the superconducting world, not all of whom are apparently working on superconducting solutions. So you've got a hypertech appears all over the place, but they're providing cryogenically cooled conventional motors as well as superconducting versions. But this one in particular is definitely a superconducting version. So superconducting is there and is being considered. And it's important to this program. As I say, this program, as it's voiced, can be done with conventional technologies, but if you need to get to the final solution, you need superconducting technologies. That's what they will be building, something similar to that. So the idea is you have multiple fans, and the fans can all be operated at different times. And you also have fans on the wingtips. I'm not going to go into this in detail, but there are lots of different designs which are all essentially similar, but they all rely on a multiple fan solution and at least one gas turbine. I love that video. It's approximately 10 years old, or might even be longer than that now. We collaborated with Rolls-Royce and with Airbus, and the eagle-eyed amongst you will have noticed that there were superconducting bulks in their mock-up. It's a concept, that's all. I'm not going to go through that, except to say we've got a long way to go. If we're going to get anywhere near our 20 kilowatts per kilogram, then we need to be up here. These are estimates, they're not reality. Somebody's decided that that might work. The closest we got was in 1977 with a Westinghouse machine. And there's the Rolls-Royce motor. That was at the Paris Air Show. We're very proud of that. So there's superconducting bulks there. They're slightly unrealistic. They're somewhat larger than you would actually build. And actually the standard bulks have now been supplanted by so-called artificial bulks as well. And they've featured in another program, which I'm going to show in a minute. So this is the program. This is the most recent all superconducting motor, which is called Assumed. Again, we have an acronym. It's an Advanced Superconducting Motor Experimental Demonstrator. They were targeting a 1 megawatt machine having specific power density of 20 kilowatts per kilogram. So not quite the 2 megawatt machine which the Rolls-Royce man mentioned initially, but it is in theory a beefy motor. And it was based on artificial bulks and normal conductors. The program finished last year, and I think they got some good results, but they didn't get anywhere near a 1 megawatt machine with specific power density of 20 kilowatts per kilogram, unfortunately. We have it in our lab now. If anybody wants to see it, they're welcome to come and visit us, because we actually have the machine they built in our lab. So what were they trying to do? They were trying to up the electric loading, because you have to up the electric loading in order to get more power. And they were trying to up the field. So that is fairly straightforward. We know that superconductors can probably achieve that. That's much more difficult to achieve that 2.5 Tesla. But in theory, they could have done it. And it's not an unreasonable target. And as I say, the program's just finished, and I do hope that we can pick it up again with the demonstrator they built. They're talking about a thermal loss of less than 0.1%. I think that's really rather ambitious. So here you go. This is an animation done by Francesco Grilli, who is a good friend and I think a great scientist. And the reason why I put this up is because you can kind of see the problem. So the red and the blue areas represent current into the page and current out of the page. So you can see that if you've got a superconductor and there's a changing magnetic field on the superconductor, so you can see the flux lines going round, then you will end up with changing current. You will end up with an AC loss. And this is the thing which has held us back massively, because you can't really afford an AC loss of 20 Kelvin of any magnitude. And you certainly can't get anywhere near a 99.97% efficiency. So this is the problem we need to solve if we're going to have superconducting motors. I'm not going to bother with this, except to say that I might be depressing you guys by telling you how difficult superconducting motors for aircraft is. But it was a video, which I'm not going to show, of EchoSwing. And EchoSwing is fantastic. They did the full marketing thing. They took an existing generator off a wind turbine nacelle, and they replaced it with a superconducting one. And it's such a brilliant piece of marketing, and it just shows you exactly what you're gaining by having a superconducting machine. The blue bit is a superconducting machine. The red bit is the machine it replaces. And it's obvious to everybody or anybody where the advantage lies in terms of weight. I'm not going to do that as well because I'm running out of time. But this is a couple of slides that Min Zhang put up at UCAS a couple of years ago. That she went through 3 designs, all at 2.5 megawatts. All at
sorry, Tim. Sorry,
well,
Tim. We have 5 minutes.
Yeah, I know. Thank you, Zia. I've nearly finished. Why do you think I jumped? Don't worry. The point is that what you have to look at is you have to look at these numbers. And you have to look at the fact that if you reduce the size of your tape, if you're using HGS, or for that matter, you reduce the size of your filaments if you're using MGB2, then you reduce the AC loss. And those are her predictions. So she predicts that she could get the loss down to 99.5% with 0.25 millimeters. And she's actually been quite honest here because she's taken that 99.5% and said, but that's actually 95% because we're going to have to cool it. So that's the state of the art. The problem is that to get to 0.25 millimeters with HGS tapes, for instance, you've got to pattern them. And generally speaking, if you pattern them by using striation, then you damage the critical current and you end up back where you started. So our latest project, and what we really are hoping that we can do, is we want to take we want to steal all the work from the past few years and take the Röhrbull cable, take the cork cable, take the fact that we know striations will reduce losses, right? And redo it all, and redo it by taking a single tape and patterning it. So what we do is we take a tape and then we etch it, and then we'd lay some more superconductor on, and then we'd etch it, and we'd lay some more superconductor on, etc. And we could, by doing that, or we think we can, but the program's fairly early days, create a Röhrbull cable in one single tape that in principle can be, the techniques can be put straight into the manufacturer's manufacturing equipment with a few additions, and we can manufacture Röhrbull or Rutherford cable type flat cables. And hopefully we can do that. If we can do that, or if somebody else can do something similar, then maybe we can have superconducting plane. So I think I'll stop there. Have we got any questions? No. Okay. Right. So that was me. We haven't got any questions. I've got 3 minutes in principle to answer questions if somebody wants to answer questions. I will do what I told everybody else.
Tim, we have a question from
Oh, we have. Oh, go on.
Do small ships inland shipping, that's from Nitin Ray, not from me. Do small ships inland shipping offer a route for assisting the commercial development use of motors and associated control and management system, essentially a catalyst for reducing some of the risk challenges inherent in the aviation sector?
Okay. Yeah, no, that's a very good question. And there is a lot of investigation being done on small ships. I mean, I'm working with a Norwegian oil company. We're doing a study on battery backup systems in electric ships. At the moment, what they're tending to do is they're tending to concentrate on conventional machines to couple with diesel generators, which is what they'd have to have, and batteries. And the idea is to reduce the load on the diesel generator. But yes, you're right. That is potentially a good way into it. And ships could, in principle, be a good route. But why not? Why bother with ships? Why not go to the real prize? Why can't we shoot for aircraft engines? I mean, I like a challenge, don't you? Yeah. Okay. All right. Airships. Okay. He's put airships. Yes, you're right. Airships. But yeah, airships is definitely a compromise. Do we need it for airships? I mean, we can kind of build airships already. If we're happy to travel slowly everywhere, yeah, airships. But it's there. Isn't it? Do we need any changes in order to achieve airships? I don't think so. They've been around since the Hindenburg, haven't they? Oh, cargo transport. Okay, you keep on adding things on. Look, yeah, there are lots of different avenues that we can explore. And as I told you, ARPA-E is looking at electrification of transport. And I think that this is an interesting and active research area. I also think it will keep me going for the rest of my life, and possibly the youngest of you here going for the rest of your life as well. So I am a natural born pessimist because I know that there are lots of problems. Anyway, I must pass over to Jamie because it's now time for Jamie's talk. Jamie works for Tokamak Energy. Have I stopped sharing it?
Yep.
All right. Jamie works for Tokamak Energy, and he's going to give us a talk on how you can make a fusion magnet with sixpence.
All right. Thanks, Tim. So can you all see these slides? Just quickly. I'll assume that you can and hear me. So thanks so much. So yeah, my name is James Garwood. I'm from Tokamak Energy. So it's a company out from Oxfordshire. So I'm calling you from our office today. And this presentation will hopefully show you how high temperature superconductors, or specifically REBCO superconductors, are a bit of a game changer for nuclear fusion, and how Tokamak Energy is sort of leading the pack in this really exciting development. So I hope you enjoy. First, we'll go through what fusion is with a bit of an overview, as I know this isn't sort of a fusion energy conference. Then we'll look a bit more closely at why REBCO superconductors have been creating a bit of a stir in the fusion community. I'll spend a good portion of the time highlighting what TE, Tokamak Energy, is doing in this space. And hopefully we'll end with a summary of public and private fusion efforts. This hopefully will leave a bit of time for questions and discussion at the end. Okay, so what is fusion? Well, most of you will know that it's the combining of two lighter atoms into a heavier one, and that this reaction can produce energy. Let me just pull up this pointer. This, of course, is the opposite of nuclear fusion, nuclear fission, on which current nuclear plants are based. So that's splitting of heavier elements like uranium into lighter ones. Other sort of important key points to remember are that of all the possible fusion reactions, the most promising one is this one here on the left. So it's a fusion reaction between two isotopes of hydrogen, deuterium and tritium. So that's hydrogen with 1 and 2 extra neutrons respectively. Now, for most people, especially mere engineers like me, knowing sort of the reaction and the basics of it is plenty of detail already. There's always more sort of deeper levels to understand it, but I won't go too far into it today. One more thing to remember though, is that these are nuclear reactions rather than chemical. So the energy per unit mass is much, much higher than a chemical reaction. So for example, burning a ton of coal is similar to a kilogram of this DT fusion reaction. Okay, so this all sounds good, but why else are we interested in fusion? Well, firstly, and perhaps most importantly, fusion reactions are intrinsically safe. So unlike fission reactors, where you need sort of a significant amount of fuel all together in the same place to reach a critical mass, in a fusion reactor, you'll only be using a few grams of fuel at any one time. So there's simply no chance of a runaway reaction or a meltdown. Second, the primary fuel sources, this deuterium and tritium that I've shown you before, are both cheap and abundant. So deuterium can be produced from seawater and tritium can be produced from lithium. The primary product of the reaction, if you saw before, was helium. So that's not radioactive, so there won't be any long-lived waste products from the reaction. And nor, of course, will there be any CO2. Now, I hear you say, won't the world be powered by renewables like wind and solar by the time we develop fusion? Well, perhaps we'll be well on the way, but population and energy demands are still increasing, and fusion provides something that these can't in the form of having a small physical footprint. So it's a very dense form of power, and it also is able to provide baseload power without sort of any energy storage. So simply put, if we take a long-term view, if we can get the technology to work and really tame the physics, then fusion would constitute a near ideal energy source. So why aren't we doing this? Well, actually, we certainly can produce fusion reactions, and we've been doing so for many years in labs. The trouble is that we need to sustain a useful reaction for long enough without using more energy to heat and contain our fuel than we get back from it. So a simple but widely used way to think about this is that you need to keep your fuel, whatever it is you're trying to fuse, dense enough and hot enough for long enough. This can be expressed in an equation here, known as the triple product. So that's just a product of these three things: N, the density, capital T, the temperature, and tau, the confinement time, how long you keep your fuel and your energy together. If the product of these three things is high enough, you'll get a useful fusion reaction that can produce energy. So if we take a quick look at perhaps the most famous fusion reaction in our solar system, that's the sun. The fusion fuel is obviously both very dense and very hot at the core of the sun. The particles, the fuel particles, are kept together or confined by gravity, and the only energy is lost right at the edge of the sun to radiation. So it also has an excellent energy confinement time. However, so practically on Earth, there's no way that we could reproduce such a good fusion reactor. We couldn't match the triple product of the sun. But this isn't where the story ends, because the sun uses as its fuel source protons, so that's just hydrogen with no neutrons, and the reactivity of this is very, very low. So we can be a bit clever, and here on Earth with our fusion reactors, we can use fuel with much higher reactivity, these isotopes of hydrogen, deuterium, and tritium mentioned before. And actually with this advantage, we do quite well. So this figure on the right here is the masked spherical tokamak just down the road from me now in Oxfordshire. And in this type of reactor, we can actually achieve even higher temperatures than the center of the sun and get a pretty decent fusion triple product. So how do we do this? Well, the most promising way to achieve these conditions is to trap your fusion fuel, which when you heat it up enough, becomes an electrically conducting soup of hot ions and electrons called a plasma. You trap this using a magnetic field. You do this with these toroidal field coils. There's these ones here in blue. And you can see that the field produced by these actually makes a ring or a torus that closes in on itself. You then have the plasma, which is sort of shown here in pink or purple. And we know that these electrically conducting sort of ions and electrons can't cross strong magnetic field lines. So they're confined within the torus, even when heated to extreme temperatures. Now, there are other ways to achieve fusion, including other magnetic confinement schemes and completely different looking ones that use lasers to implode small targets. We won't go into them here, but I will mention them briefly at the end and include some links for those who are interested in going down the fusion rabbit hole. Based on the name of my company, of course, you can guess that most of this talk will focus on these tokamak machines. Now, rest assured, though, that tokamaks do hold all the records for fusion triple products, and based on current evidence, they're the most likely road towards practical fusion energy here on Earth. So how close are we? Well, not as far away as you might think. So this graph on the right here shows that between 1970 and about 2000 or so, there was a sustained period of really rapid progress in fusion that brought us right up, this is the fusion triple product here on the y-axis. And by the late 90s, we were right up here at the break-even level, where you have about as much energy back from your reaction as you're putting in, and not too far away from ignition, where you'd have a self-sustaining fusion reaction that wouldn't require any input power at all. So what happened? Based on this graph, surely we've broken these records and we have fusion plants running. Surely we're up here somewhere by the 2020s. Well, unfortunately, these records actually all still stand. And one take on why this has happened is that the progress until the late 90s up here had largely come from increasing the machine size. But by the time we got up to this point, these machines have become enormous, expensive, the size of a national lab. And to take the next step, it would require a device of vast size, complexity, and expense. And here is that machine, the International Thermonuclear Experimental Reactor, or ITER. This machine is currently being assembled in the south of France and is specified to go well beyond energy break-even and produce significant fusion power. There's even a chance that ITER could produce an ignited plasma, which would be pretty spectacular. Now, not only does ITER make the claim to be the most complicated machine ever built with the strongest ever superconducting magnets, that's a stored energy total of around 50 gigajoule. It also has sort of largest vacuum vessel and largest cryogenic plant ever, and so on. But one of the key things is that it's also one of the biggest collaborations ever. So it's got China, Russia, Japan, Korea, India, the EU, and the US all collaborating together. Now, getting these countries to agree on anything, let alone building something like ITER, is an accomplishment, but it's not exactly a recipe for efficiency. And this is a really key part of why progress has been so slow. Indeed, it's taken several decades to get to this point of ITER. So it's currently under construction. And the burning plasma experiments won't be taking place until 2035. Still, we shouldn't be too critical of the project. If it's successful, it would be a huge step forward. And while it won't ever power any homes, ITER will qualify all the key technologies needed for a fusion power plant. But 2035 really is a long way off, and people working in fusion are rightly impatient. So is there a better or faster way to fusion energy? Well, for magnetic confinement, as you might well guess, the fusion performance, and this is the fusion triple product here, gets better with higher magnetic fields, as you can sort of see here. And it's not just a bit better. As you can see, it's to the cube or the third power of magnetic field. So that means a very modest increase in magnetic field can give you much better fusion performance. Or more importantly, you can reach ITER-like performance with a much smaller device. And I think this graph was shown on Ziad's slide before. So keeping your target power of 500 megawatts, if you increase the field from about 5 Tesla to about 9 Tesla on the plasma axis, you can make the machine volume about 10 times lower. Now, if we keep this in mind, is there any other way to improve performance? Well, looking back at our equation for triple product, it turns out that the plasma shape is also very important. So these parameters in the equation, kappa and A, basically describe how the plasma is shaped. And it turns out that if you shape your plasma more like a cored apple rather than a donut, you get a number of advantages. So firstly, a higher triple product, so better fusion performance. But you also get an advantage that plasmas of these shapes require less external current drive to stay stable. Hence, they'll use less recirculating power to operate. And so they're a much better candidate for a fusion power plant than sort of a conventional aspect ratio device. So what happens when we put together this desire for both high magnetic fields and spherical tokamaks? Well, it puts really high demands on the conductor forming the machine magnetic field. So you can see from the machine geometry here that if you've got this cored apple shape, there's not much room down the center. So not only does your conductor need to operate in high magnetic field, it also needs to operate with very high engineering current density. Additionally, the conductor almost has to be a superconductor, otherwise you'll end up using most of the power you produce to drive your power supplies and cool down your conductors. Now, if only we knew of a relatively new superconducting material that had all of these properties. And so, after a rather convoluted introduction, here's a material that a lot of you will be familiar with. That's Rebco at the top. Now, Rebco is best known as, we've seen these slides at least a couple of times before today, and you'll be very familiar with it. So Rebco is best known as a high temperature superconductor, but obviously what's important for fusion is that it retains superconductivity at high magnetic fields and high current densities. And just as important is the fact that these days we can now get large quantities of this conductor available from several different manufacturers in reasonable kind of quality. So this really is a game changer for fusion. And so this is it. and this is Tokamak Energy's pitch really, high field spherical tokamak fusion enabled by Rebco high field, high current density superconductors. Now, what are we doing? Firstly, this is all very much more than a paper study. So in our site in Oxfordshire, where I'm calling you from, we have a world-class spherical tokamak, high field spherical tokamak ST40, which is currently on a campaign to hit plasma temperatures of 100 million degrees. Now, this is not a superconducting tokamak, so these are copper coils, but it is the highest field spherical tokamak currently in operation. So ST40's already had some fantastic results, and it's well on our way to our targets. So watch this space. But we won't be satisfied with that and are planning a massive upgrade for ST40, or major upgrade for ST40. We want to increase the magnetic field even further, up to 3 Tesla on plasma axis, with liquid nitrogen cooled but still copper magnets. And this is part of the chiller system that's recently been installed. And we'll also be doing many other things like installing or ordering an RF heating source of 2 1 megawatt gyrotrons. And so these can be both used to further heat the plasma, but also drive current that it requires to stay stable. Loads of other upgrades to push the limits of the device and push the triple product we can get. So onto superconductors, we have a brilliant team dedicated to the development of these Rebco magnets. So this effort started off with small magnets, small sort of test magnets of less than 1 kilometer of Rebco. And this was really to verify conductor quality and our modeling. It also let us build a lot, test a lot, and fail fast, and really unlocked our key technology advantage of partially insulated or non-insulated and then partially insulated Rebco magnets. A lot of you will be familiar with this idea, that you have sort of a conductor or a partial conducting path between the superconducting turns of your magnet, and these are much more resilient to defects, and it can be self-protecting in the event of loss of superconductivity or quench. You can actually see, here's quite a nice one here, you drill some holes directly through these non-insulated magnets and they can still operate reliably at slightly reduced field. So this is an incredibly robust technology in addition to being able to hit those targets of high field and high current density. This has even led to some really exciting results. So our demo 3 magnet, this one here, it's just a non-insulated Rebco solenoid with a modest bore size, quite a small bore size, demonstrated over 24 Tesla at above 20 Kelvin operation. So we think that this is the first time that these types of field were demonstrated by an all superconducting magnet at these sort of more practical temperatures, well above the boiling point of liquid helium. So while this is brilliant for our fusion program, it's also clear that these magnets will be a game changer for other applications. We've recently signed a deal for technology transfer with the Paul Scherrer Institute in Switzerland and talking with many other industry, government, and academic groups. So if anyone's interested in this, either for fusion or other applications, feel free to reach out and get in touch. So we also know that we need to scale these magnets up for fusion. And for this, we have demo 4. So this will have a full set of tokamak toroidal and poloidal field coils. So the toroidal field coils and a couple of poloidal field coils here and here. Now, this will demonstrate most of the key technology hurdles for integrating Rebco magnets into high field spherical tokamaks. And while this machine will not have a plasma mission, so it's just to verify the magnet tech separately, it will be a first of a kind on many fronts in terms of field on conductor, stress on tape, stored energy, and so on. Right, and this isn't all. We're also looking forward to Reactor to develop key technologies. So to reduce recirculating power from our superconducting magnets, we're developing a cryogenic power supply, so power electronics operating at cryogenic temperatures, to deal with extreme heat loads from the plasma and extend the reactor lifetime. We're developing first wall components down here, and even looking at the use of liquid metal walls for our tokamak. all this will feed into the design of an optimized future reactor for the purpose of generating electricity. And so we're grateful for the support of both the UK and the US government for especially these programs, having secured competitive grants from both BEIS and the Department of Energy in the States. Okay, so that's basically it on the tokamak energy front. But before we get into questions and discussion, I think it's worth sort of zooming back out again to look at this in context. So fusion is a huge field. It's been pursued by governments large and small for a long time. And this world map here on the right is from a database, government database of publicly sponsored fusion devices collated by the International Atomic Energy Agency. So a link to it below that I might pass out later. You can see that there are almost 100, or in fact over 100 government fusion devices across the world, and that most of these are tokamaks. So 64 out of 102 are tokamaks, but there are a few others, including stellarators, laser fusion, and some alternative concepts. So some of the main ones to watch for are here on the left. So the JET tokamak in Oxfordshire, which is just down the road from us here, will be looking to break fusion power and energy records later this year in support of ITER. On the same site, the MAST-U tokamak has just released some really exciting results showing how a key exhaust problem for spherical tokamaks can be solved. ITER itself, of course, gets a mention, and watch out for first plasma in 2025. And interesting non-tokamak efforts include the world's largest superconducting stellarator, W7X in Germany, which is undergoing an upgrade to run 30-minute plasma pulses. And a sort of non-magnetic confinement, we have NIF, the National Ignition Facility in the States, breaking records for their laser fusion. And they're still aiming for plasma ignition with that system. And then in the New Mexico desert, the Z machine is breaking records for magnetized target fusion, which is sort of combines aspects of laser and magnetically confined fusion. So these efforts really are pushing the boundaries of physics and our understanding, and also on the technology fronts. But the private sector also has a really important role to play. So we drive innovations and also have to ask ourselves the hard questions to survive, like how we can turn all this very interesting plasma physics and technology into a real product. So there's a growing number of private fusion ventures. And again, this is from the same database, but now privately funded efforts. Perhaps unsurprisingly, a lot of these are in North America, and a lot of them are based on alternative concepts. Quickly, just the big players. You've heard about us, Tokamak Energy, so and how we're sort of advancing spherical tokamaks and Rebco enabled by Rebco superconductors. We have some friendly competition across in Massachusetts with Commonwealth Fusion, who also think that Rebco is the way to go, but are applying a conventional aspect ratio tokamaks. Over in California, we've got Tri-Alpha Energy, and so they're looking at beam-driven magnetic confinement fusion, but also hoping to use a different fuel source. And finally, you may have heard in the last few weeks, actually, that General Fusion, a Canadian company, is going to come to this Oxfordshire site to build an experimental reactor in the UK. There's something of a dark horse in the fusion race, and rely on mechanically compressing a plasma with liquid metal walls, which is something that no one else is trying to do. But the point of this is that all these private fusion ventures are generating competition, opening up new funding channels and different incentives to develop fusion faster. And they're really stimulating innovation. So this can only be a good thing. Okay, so just to summarize, I think we're still okay on time. So fusion could be an ideal energy source. I'm going to say when we get it to work, as it's fairly clear that we're getting very close to practical fusion, and ITER will almost certainly demonstrate energy break-even and possibly ignition. Rebco superconductors are enabling smaller, faster, and cheaper fusion, and Tokamak Energy is right at the forefront of this effort with our operating high-field spherical tokamak and record-breaking Rebco magnets. Public and private fusion efforts are driving real progress, and it's an exciting time to be in the field. So on that note, thanks. And any questions or discussion in the breakout room? Thank you.
Okay, thank you ever so much, Jamie. Don't go to the breakout room just yet. because while you're all thinking of your questions and putting them in the chat, what we're going to do is we're going to take a quick picture of the audience. So can I ask you all to switch your cameras on? At the moment, it'd be a very boring picture. Getting there.
Thanks, Tim. I'm just going to set that up now. So just give me 1 second.
Of course. Do we have any more people who are going to switch their cameras on? John Durrell, don't be shy. No? John Durrell's going to be shy. But he's not.
There's definitely room for a few more if you want to put your cameras on.
Oh, Yang, don't be shy. Jintao, don't be shy. Luning, don't be shy. Rocco, don't be shy. In the meantime, please think of your questions while we're setting this up. Okay, that's probably, everybody else is probably either not really here or don't want to show their faces. So Nadia, can you go ahead and take the picture? Yeah.
Okay, there's just a few more loading up now. So
All right, okay, we've got some more, yeah.
just give it a second. There's one just connecting. And another one, yeah. I think Lunning How is trying to connect. Oh, they're gone. Okay, so Tim, if you're happy to go now, I can.
I'm not happy because your camera's not on.
My camera.
Well, why not? You've helped organise it.
Well, if you want me on, I will. Oh, wait, there's another. Yeah, there's Lunning How is coming on there. I'll put my video on.
Thank you, Nadia.
Anyone else? No? Okay. All right, I'm going to do this now. Okay, when you're ready. Okay, so just tell me when you're ready.
We're all ready.
Okay. 1, 2, 3. Is
that it?
Yeah, that's it.
Thank you ever so much, Nadia. Do we have any questions for Jamie? Yes, we do, actually. Nitin Rai has said, is there a theoretical limit to how small these machines can get? Is it capital cost as the main limiting factor in going for even larger machines? I think that's to Jamie. It might have been to me. But the next question, which is definitely to Jamie, which is when you get it to work, won't the neutrons destroy the first wall material except the liquid metal version, which seems a bit unfair, Jamie. Can you rebut
yeah, well,
that?
So I think those sort of, assuming that first question was also for me, I think those are quite linked. So how small theoretically can you make the machines? Well, it depends less on theory. Obviously, if you get excellent confinement, there's very little sort of theoretical limit on how small you could make it. But practically, because as the second question has alluded to, you've got these high energy neutrons streaming from your plasma, you basically have to shield it. You have to have a first wall material and a neutron shield that will cope with that, which will be on the order of towards a meter behind that. So effectively, there's a practical limit on how small you'd want to make the devices. In terms of first wall and so on surviving, so there's definitely a question about lifetime. So definitely, or almost certainly, you'd have to have a maintenance scheme where you'd replace those first wall components, but certainly they can survive kind of first, they can survive full power years, but perhaps not the whole life of the reactor. So I hope that answers at least partially those two, that you would, because of this neutron problem, you are sort of, there's a sweet spot for device size. Obviously, you don't want to get too big because your capital cost will balloon, but it has to be some minimum level to have an adequate lifetime.
Okay, Ahmad Baker has asked, where can I find a recording of all of these talks? The IOP have been recording it. I believe they will make it available, but we'll send you guys details if they are available. Right, so the final talk, but obviously not the least talk, is going to be given by Shabazz. And where have you gone, Jason? Because you're supposed to introduce him. So I will pass you over to Jason, who will introduce Shabazz. And then after that, we will have a summary of the day by Ziad. So thank you all. I might pop up later, but otherwise I'm very, very pleased with the speakers. And I'm also very impressed by how many of you have stuck the course. This was an experiment, and apart from the breakout rooms, which didn't really happen, I think it's worked. Okay, thank you. I'll pass you over to Jason.
Thank you very much, Tim. So Shabazz Anvar on the screen will be giving a presentation this afternoon about my group's research on so-called superconducting spintronics. Before I pass over to Shabazz, I'll just say a couple of words about superconducting spintronics. So this all started really during my PhD under Professor Mark Lemire when we were making Josephson pi junctions. So this is Josephson junctions with ferromagnetic barriers. And what we demonstrated is that if you use transition metals such as cobalt, iron, and nickel, you actually get very large critical currents. And these critical currents oscillate as a function of ferromagnetic barrier thickness, and for dilute ferromagnets as a function of temperature. And this is fantastic because it means you can create a device in which you effectively build in a phase with a magnetic exchange field. So unlike a conventional squid where you might have a superconductor, non-magnetic superconductor junction, you no longer need to apply a magnetic field in order to cause a phase shift between, for example, 0 and pi. In more recent years, we've been looking at Josephson junctions in which junctions don't only transmit charge in the superconducting state, but also a net spin, so-called Josephson triplet junctions. So at this point, I'm going to pass you over to Shabazz. So Shabazz is a senior postdoctoral scientist in my group. He did his PhD with a very well-known person in the field called Professor Jan Arts at the University of Leiden. After his PhD, he moved to Japan, where he was a Japanese research fellow, or JSPS fellow, sorry, working with Professor Yoshi Maino on oxide superconductivity, and in particular oxides which are thought to have an unconventional superconducting state. So the particular material Shabazz was working on in Kyoto was strontium ruthenate, or strontium ruthenate 214, which until fairly recently was suspected to be a P-wave superconductor, although that's now a hotly debated topic. So on that point, I'm going to pass you over to Shabazz. So many thanks, Shabazz.
Thank you very much, Jason, for a very kind introduction. So as Jason already mentioned, that I am going to talk about superconducting spintronics, mainly focused on the contributions that we are doing at Cambridge, and those already also happened in the Cambridge. So in fact, the Cambridge is contributing in this programmable computing since the beginning. For example, here is the picture of the first calculator developed by Renwick and Sir Wilkins in 1947. So this calculator was so huge that it really need a full one lab. And this system was working on mercury delay lines as memory, and derated vacuum tubes for logic. So this system was consuming about 11 kilowatts energy, and its multiplication time was about 6 milliseconds. So since then, we know that the progress in computing and in computers and computers, so it was so rapid that it also actually reduces the sizes of the computers. What on the other hand, it actually also, you could say, that increases the size of the data centers. So nowadays we have the data centers, as you can see here. It's a huge data centers. So about 10 to 15 years ago, that these data centers, they were mainly processing the emails or you can say storing the information. But then with also processing the information, so the requirement and the size of the data center was actually exponentially increasing. At this point, all over the world, we have about 500,000 of data centers. And by the next year, or maybe you could say that at the end of this COVID year, that maybe it is already actually double. So in these data centers, the main technology that we are utilizing is the CMOS, a complementary metallic oxide semiconductor. So this technology is working so far for actually the energy storage and processing there. And then the increase in the requirement of the data centers, or the number of data center, is here. You can see in this graph that it is actually linearly increasing every year, and it will, of course, will continue increasing. And this increase in the number of data centers also increasing the requirement, or you could say, is an increase. There is an increasing demand of the electricity for running these data centers. And for example, in to run these data centers, we need about 4% of the total electricity generated within the Europe. And out of that 4% electricity is only used to keep these data centers cool. So then it means that we are in fact not only consuming a lot of energy, but we are also contributing in energy dissipation, which is contributing in carbon emission. So to actually, because as I already mentioned, that these data centers, they are working with CMOS technology. So to address these questions related to energy efficiency, that what could be the role of spintronics, for example, the electronics that actually exploiting the spin. So this here I will show you the timeline of the spintronics, that we know that the spintronics was actually initiated with the observation of giant magnetoresistance by two Nobel laureate, Professor Grunberg and Professor Fact, in 1987. So then, based on their observation of giant magnetoresistance in 1991, the spin valves were developed. So where we actually use two ferromagnets and non-magnetic, which is sandwiched between these two magnets. So then in this structure, the transport properties are actually dependent on the spin alignment of both of these ferromagnets. So you can switch your resistivity by switching the magnetization parallel to the anti-parallel. So then in 1999, then there was another, actually the phenomena that is the spin transfer torque, means the switching of the magnetization through the spin transfer torque was also observed. So this was also very important, that you need, you can actually push a spin polarized current, which can actually transfer the momentum and can switch your magnetization from one direction to the other. So it depends that in which direction your polarized current is going there. So then I guess, yeah. So, and then not very late in 2006, the spin Hall effect was observed. So this spin Hall effect, what we do, that we do have, for example, a ferromagnetic layer, and which is actually connected with a non-magnetic normal metal layer. So by pushing the current in the ferromagnet, that can actually give the spin imbalance, or spin current, in the normal metal, and it can actually induce the voltage, meaning that this is because of the spin splitting in this normal metal, which is actually giving us the charge imbalance, which is inducing the voltage, which is coming because of this you can say the spin-dependent transport at the interface. So this spin Hall effect was observed in 2006, and then recently antiferromagnetic material-based spintronics was also initiated, where antiferromagnetic materials can be utilized for switching from one state to the other. So this could also be actually utilized for memory devices. So currently we already have this STT MRAMs. So STT means spin transfer torque based MRAMs. Those are already actually, you could say, available there. And then now let's have a look that whether they are efficient or not efficient, and what could be the actually the you can say the competition with respect to the CMOS technology. So as we see that we actually in this spintronic devices, what we do, we are actually switching the state from parallel to anti-parallel or anti-parallel to parallel state. So for this process, the minimum amount of energy which is actually you could say given by the magnetic anisotropy, and this energy at room temperature is about 10 raised to power minus 19 joule, and at low temperature it would be minus 21 joule. But in case of the CMOS devices, that actually corresponds to is of the order of 10 raised to power minus 16 joule. And here we can see that it is actually 4 to 5 orders actually, you could say, more efficient this spintronics. What, as we already actually I mentioned, that for switching, particularly the electronic switching, we need spin current. And for generating spin current, we need a large charge current. And that charge current, which we actually need for spintronic devices, it dissipates, of course, the large current will dissipate the large amount of the heat energy, which corresponds of the order of minus 15 joule. And this dissipation, of course, again, the loss of the energy, and it could also contribute in carbon footprints. So then now we can think that can we do this spintronics with a current that could be dissipationless, meaning that sort of a zero resistance, and the zero resistivity we could achieve in superconducting materials. So can we do spintronics using superconducting materials? So yes, it could be possible. So then here you can see that the IBM recently actually started this 3 billion project to do superconducting computing, meaning developing the computer based on superconducting technology and based on superconducting devices. But on the other hand, we can also do, for example, this computation using the single flux quantum. What in single flux quantum technology, we need microsquares. So then this sizability could be an issue there. So then let's have a look on the timeline of superconducting spintronics. The superconducting spintronics, in fact, started with the idea of Josephson junctions that was actually first given by Professor Brian Josephson and from Cambridge. So the idea is that if we connect two superconductors with a barrier, and that barrier can be an insulating, and through this insulating barrier, we can tunnel the superconducting, you can say, the particles from one side to the other. And so in this way, we can develop a junction, and that junction is the transport properties of this junction is depending on the phase difference of these two, would say, the superconductors. And then in 2001, there was a new development, and that development was the pi junctions. So pi junctions means that what we do have, we have a superconductor. For example, in this example, that was done by Ryazanov in Russia with the collaborations of Leiden, the Netherlands, my previous group. So there they actually connected they have two superconductors, niobium, and a copper nickel ferromagnet, which is a weak ferromagnet. It is actually providing a weak link between these two superconductors. So here you could see that the phase of the system is oscillating oscillating from 0 to pi by changing the thickness of the ferromagnet. So this idea can also actually can be utilized to develop phase batteries. So then in 2004 at Cambridge by the Professor Mark Blamer, so they developed superconducting devices where they do have two superconductors. And here the barrier is in fact like a spin wall, that we do have two ferromagnets and then there is a barrier in between. So the transport properties of this device depends on the alignment of magnetization of these two layers. And here you can see that these black circles, they are representing the critical current of this device, which is actually switching from anti-parallel to parallel state. And this red one, it is the resistance of the system. So you can see very clear switching. So here the one point, so this kind of technique, a technology, you could say, can be utilized to develop cryogenic memory devices. And here, the thing that you may note that both of these works, there is the main thing is that the charge transport. So these are based on the transport of the charge rather than the spin of superconducting particle. When I say superconducting particle, that means the Cooper pairs. So then something very interesting happened in 2010, where Professor Robinson, he observed spin polarized supercurrents. So in this spin polarized supercurrents, they used multiple multi-layer ferromagnets as a barrier between two superconductors, which is generating the spin polarized supercurrent. And in my next slides, I will go in more details that how we actually can do this. And at the same time, there was also two more groups, one from Leiden, where I was actually doing my PhD at that time, and I was the part of that project. So I was trying the same kind of things with half metallic ferromagnets. And the third group was from Michigan State University. So they also utilized the multi-layer ferromagnets and observed this spin polarized supercurrent. So here in this figure, you could see that if we are using the single ferromagnetic layer, then critical current in the device can actually die off quickly with the increase in the thickness of the ferromagnet. But if we do have multi-layer ferromagnets, then it actually is not dying off. So it's actually staying even for a thicker total ferromagnetic barrier. So then in 2014, again from the Cambridge University, so there the spin selectivity of the spin triplet Cooper pairs was actually observed, where multi-layer ferromagnetic and a superconductor system used. So this system is like, you could say, superconductor ferromagnet bilayer like system, but this ferromagnet is a multi-layer. So, and the last layer is an anti-ferromagnet, which is fixing one ferromagnet, and other ferromagnet, which is a permalayer, you can switch its direction for observing spin selectivity. And then this superconducting devices based memory devices were developed in 2018 by North Grumman Corporation. So there they utilize this charge-based technology, and they are actually reading or writing the information using these microsquids. So again, these are the microsquids. So then scalability could also be an issue in these devices. So then now the question that how we can induce or put the spin in the superconductor, or we can have this spin polarization with the zero resistance for our charge current. So here, let me give you an example of a superconductor. That in superconductor, we do have a Cooper pairs, as you know, that both have a opposite spin. So total spin of a Cooper pair is 0. And if we connect with a ferromagnet, but there the spins are aligned, and we have a spin polarization, because in the ferromagnet, there is a spin splitting. At the Fermi level, we have different spin density of state for spin down and spin up. And if we put this Cooper pair in this ferromagnet, then we actually, our Cooper pair can gain the momentum because of this mismatch. So total is not 0. So we are getting some, our Cooper pair will get additional momentum. And because of this additional momentum, the correlation which is induced in the ferromagnet will actually have the additional oscillations. And these oscillations are also the change in the phase of the correlation. And secondly, that the exchange field of the ferromagnet will kill this kind of a superconductivity, because the ferromagnet would like to align the spins. So this superconductivity will die off very quickly in a ferromagnet, but within few nanometers, even for a weak ferromagnet. And then here, one more point that I want to raise here, that here at the interface, what's happening that we do have a spin singlet Cooper pair, but we do have this spin splitting. So because of the spin mixing at the interface, we can also have spin triplets, but these spin triplets are with zero alignment, meaning that their alignment is perpendicular to the quantization vector. So these are also actually will die off quickly within the same range as the spin singlet will die off. So then in this system, if we connect another ferromagnet to the other side of this bilayer, so this is now a ferromagnetic Josephson junction. So in this ferromagnetic Josephson junction, what could happen that here is the work from by Professor Robinson in 2006. So they are changing the thickness of this central ferromagnetic layer, and then observing the oscillations of the correlation inside this ferromagnet, which was the permalloy and cobalt. And here is the figure, the photo of the device. So main junction is here, top superconductor, bottom superconductor, and in the center we do have a ferromagnet. So here you can see that in both cases, cobalt and permalloy, you can very easily observe the oscillations in these superconducting devices. So now these ferromagnetic devices combined with the spin valves, so we can have Josephson memory devices. So here in this example, because this is again depending on the charges, meaning that the transport properties, the spin-dependent transfer properties of this device is actually being utilized to develop the memory devices. So that's why we call them the charge-based memory devices. So you can see that when we do have a parallel here means the ferromagnet number 1, which is permalloy, and the other one can be cobalt. So the Quersor field of both of these ferromagnets is different. So you can easily switch the magnetization of permalloy at a very small field, like 5 millitesla in this situation. So here you can see that in case of parallel and anti-parallel, you can have a different, you can say the critical current in this device. And this idea is being used in these Northrop Grumman memory devices. So now, if we want to have a fully spin polarized supercurrent, what should we do? So in that case, as we have already looked, that we can have M is equal to 0 spin triplet. And these spin triplet Cooper pairs can be switched to equal spin triplet Cooper pairs, where the magnetization, you could say the spin alignment of Cooper pairs is parallel to the quantization vector. And this can be achieved if we do have some kind of magnetic inhomogeneity at the interface. And this magnetic inhomogeneity actually rotates M is equal to 0 spin triplet two parallel spin triplet Cooper pairs. Those are actually providing us fully spin polarized supercurrent. And if we do have these fully spin polarized Cooper pairs, now you can see that the exchange field of a ferromagnet should not be enemy of these Cooper pairs, and these Cooper pairs should be able to stay for a long length inside the ferromagnet. For an example, that they can actually reach up to 40 to 60 nanometers in the cobalt, which is sort of the spin flip length. Because now the exchange field will not kill these Cooper pairs. The spin flip scattering can kill these Cooper pairs. So how we can achieve magnetic inhomogeneity? The magnetic inhomogeneity can be achieved using having a ferromagnetic domain wall at the interface, or non-collinear magnetization, meaning that we have a multiple ferromagnetic layer. Those have a bit different magnetization alignment. So this technique is nowadays mainly being utilized in by the different groups. And then in addition to this, we can also have magnetic inhomogeneity even if there is some disorder at the interface. That can also give you some magnetic inhomogeneity, which can switch your spin singlet Cooper pairs into spin triplet Cooper pairs to achieve fully spin polarized Cooper pairs. So here I again give an example of the work done by Professor Robinson. So here you can see that when we do have a ferromagnetic Josephson junction, but here we have only single.
You have 3 minutes left.
Yeah. Okay, so we have a cobalt, but here we have additional layers. Those are actually giving spin activity to generate spin polarized supercurrent. So you can see they can actually stay for a longer length. And then another very interesting work, which is the spin-based memory. So it is our unpublished work. And here we have, again, the same kind of the device as I introduced, that we have a Josephson junction, but in the barrier is the spin wall. But we are generating here the spin polarized current. And that spin polarized current can be actually, you could say, can be switched from the lower critical current to higher critical current by just switching the magnetization of one of the ferromagnetic layer. So this can be used as spin-based memory devices. And then the last point here is that in addition to the spin polarized charge current, we can also generate a pure spin current. That could be pure superconducting spin current, that we do have a ferromagnet. We can pump the spin, which interact with the spin orbit coupling of this heavy metal like a platinum, and it generates the spin polarized, pure spin supercurrent in this system. So this is our the current work from Robinson's group at the Cambridge University. And now here I would like to summarize my talk. The superconducting charge memory is under active development into a technology, and by mainly the Grumman. They are actually developing it very actively there. So then triplet spin current generation is already well understood. And then pure spin supercurrents have also been demonstrated, as I showed in my last slide. And sorry, I couldn't have much time to explain in more details. And then this actually all observations and understandings actually paving the way to superconducting spintronics, having, you could say, dissipation-less spintronics, energy efficient spintronics. So thank you very much.
So thank you very much, Shahbaz. I believe I'm the chair. Would anyone like to ask Shahbaz any questions about his presentation? So you could either put a question in the chat or you could put your hand up, electronically, that is.
Or we can go to these split rooms.
So there is a question from Anshuman Padhi. Apologies if I'm not pronouncing your name properly. Please go ahead with your question.
Thank you, sir. Sir, my question is like how difficult it is to like I have been working something like I have been seeing some works related to generating spin currents, and I have been seeing that it is quite difficult to first generate and second is detect. So in what order we should expect getting spin currents?
So if I understood correctly, I guess your question is not about supercurrent. It is about the normal spin current in ferromagnetic devices.
Yes, sir. Yes, sir.
So there, because we don't have any technology to directly detect the spin current. So as I already mentioned, that this the spin current, the pure spin current, we are observing using the inverse spin Hall effect. That we can induce the spin current in a ferromagnet, and that can actually give you the charge splitting. So this charge splitting giving you, you can say that is actually generating the voltage, which is coming from because of the spin current. So this voltage is quantifying your spin current, and which is not higher than a few microvolts.
Can I add a remark, Shahbaz, if I may?
Yes, please, please.
So you can actually detect a spin current. You do this by measuring a spin accumulation. And there's several ways in which you can do that. One might be, for example, in a device in which you have multiple ferromagnetic layers. And if you have spin accumulation, you might be able to apply a torque onto a neighboring ferromagnet. An alternative way of measuring a spin accumulation or a spin current is using a non-local geometry in which your voltage measurement is away from your current path. So this has been typically done in devices in which you are locally driving a charge current through a ferromagnet, and that sets up a spin accumulation in a non-local wire of, for example, copper. And then you can measure that spin accumulation as a non-local voltage signal. And groups around the world have also used that spin accumulation to spin transfer torque switch a non-local ferromagnetic element. And that's a really fascinating way of doing spin transfer torque switching, because most of your dissipation is happening at the point where you flow the charge current, but where the active devices, the active part of the circuit is fairly low in terms of energy dissipation, because there you don't have charge currents flowing, so your Joule heating is very small. The disadvantage of these non-local geometries, nevertheless, though, is exactly what you're measuring is quite complicated, because you will have heating effects, for example, Ettenhausen heating, which will complicate the transport properties you're measuring.
Yeah, but here, actually, at the end, you are measuring again the voltage.
Can I cut in? Unfortunately, I know that Ziad has to go somewhere immediately after this. So, yeah. Shahbaz, okay. Thank you ever so much,
thank you very much.
For your presentation. And can we pass over to Ziad to sum the day up? Oh. I'm sorry, Shahbaz.
No, thank you, Tim. Thank you, Shahbaz, for that excellent presentation on superconducting electronics. It's been a very interesting half a day with 6 top-notch talks about small, large, and technologies. Very active. UK is very active in it, and hence this is the motivation for the IOB superconductivity group, is really to try to bring the community together, to exchange, to share, and to develop the skill and the potential from superconductivity in the UK. UK is being a global leader in superconductivity, not just in technology and research and discoveries, as we have seen over the last 60 years, but also in commercialization. And Mohammed shared with you what MRI is doing to the UK. 40% of the global production of MRI is really comes out from here, from Oxford. So it's been really a very fascinating day, and very exciting to see really the development and the diversity of the application. I put together some slides here. Can you see my slides? Can you see my slides?
Yes, yeah, yes, yeah.
Yeah. So really, just to share, the original slide I shared with you is about the diversity of application. Although majority of them fits into the research and medical magnets, we start to see the emergence of these applications into other areas, especially on the power and energy generation, the fusion, the electric plane, the transport, and the renewables, and also into the small scale like quantum computer, superconducting quantum computer, and superconducting electronics. These two areas, the small scale, emerging worldwide, and we are expecting to see more growth, not just at UK level, but at world level, global level. So I tried here to share you how the market is changing over the coming 10 years. You could see the green blobs represent the green columns are the MRI. Is market dominated by MRI. It's almost, you could say, between 4 to 6 million. Pick whatever you want to pick from it. But the second market is science and research and development, high energy physics and physical sciences and life sciences, magnets. And the third one is NMR, basically. So these are the 3 sectors which you could start to think about superconducting market in the near term. We start to see the emergence of new applications like fusion, storage, and electric transport, and the estimated growth in these markets driven by HTS will start to show in 5 years time. And as you could see, really the market will almost increase by 4 times by 2030, and almost 40% of the increase will come from HTS if the promise from fusion and the transport and the renewables will materialize. So there's so much on HTS promise will come through, feed into these application. MRI will be steady increase, not significant, not in double digits, but a steady increase, mainly replacement of existing and expanding on new ones. However, if MRI and HTS come together to provide smaller footprint, I think that this MRI will change significantly. The other slide I want to share with you is the IP, the patents. And over the last 20 years, you could see very steady annual basically number of patents submitted, about 1,000, almost 60 to 70% being approved. And in the last 2 years, 2018, 2019, we start to see a significant increase in this patent landscape, and suddenly interrupted by the COVID. So you can see how this is up to really June 2021. And COVID really started to have an impact. Really, we suffered a little bit last year, but this year we're still suffering. But really, the trends we're going up, reflecting the interest in fusion, in particular, renewables, and the electric plane. And if I want to share with you where most of the interest and the research, you see magnetic field and high magnetic field is a big chunk of that one is the biggest blob on this number of patterns. Then the preparation method, the techniques being used, and the superconducting wire, a lot of effort is going into development of new superconducting wire or enhancing their performance, including we have also quantum current, quantum bit, Josephson junction, quantum interference. All these are really various IB, and this gives you a map where the interest and where the activity is happening. And today we more or less shared with you a snapshot where the activities on these technologies. So we estimate the expected emerging supermarket by 2030 will be on fusion. James gave us what is the current status of fusion. Electric planes, Tim gave us an overview of the 3 to 4 major projects by Americans, by UK, and by the European on electric planes, and the promise and the expectation. And superconducting storage, we touched on that, and renewables. Then give you an overview of the compact and portable high-field magnet system for physics and life sciences, where this is taking us and how the high field is driving a new class of systems and commercially provided primarily by Oxford Instruments for high field applications. And then Martin gave us a good overview on the superconducting quantum computing and how it's an area which is fast growing, over $5 billion being spent in the last 2 years. This is one of the fastest growing technologies. Mohammed Shahbaz gave us a very good overview on superconducting electronics and the developments. And Mohammed gave us an overview of MRI and diagnostic and therapy, how that will really move in the coming decade. And of course, we touched on the industrial and the transport activities. So really, today we managed to give you a snapshot and update on all these activities, and UK is very active in all of them. However, in the last week, however, in the last week, just within a week, we've seen flooding in Europe, fire California, and rain in the desert in United Arab Emirates, and the Antarctica iceberg is melting and melting very quickly. So we need a new innovation, and superconducting provide a platform for really a step change in performance, addressing the emission and the environmental challenges, will require development of advanced superconductor solution, which will provide an opportunity for at a global level as well as at UK level on commercial and environmental management. UK has very strong foundation. It's one of started the commercialization, the research at the various groups in the UK on condensed matters, new material is very strong, as well as on concentration of highly skilled workforce in the UK on superconducting technologies and cryogenic. And enhanced funding is needed at national and private to accelerate the development of advanced commercial superconducting magnet technologies. So really the community, we believe, should get together research, industry, and funding agency to start to develop a roadmap, a strategic roadmap for superconducting commercial products for the future. And I would like to thank you today for joining us and sharing with us your views. And that's my notes.
Thank you ever so much, Ziad. Thank you all of the participants who stuck with us through it, which I think we had some wonderful presentations. But thank you most to the IOP for providing us a platform and hopefully for enabling us to open the window a little bit wider towards superconducting application. Thank you all. Okay, I declare the meeting closed.
Thank you, everyone.
Bye.